All right, so let's do it. So, remember last class, we got started off on chapter 14, talking about solutions. Right? We spent some time looking at structures of molecules to try to determine whether or not they would be soluble in an aqueous solution, depending on how favorable the interaction was with water. Okay? We're going to move on. Today we're going to talk about solubility. Kind of explore that concept a little bit further. Okay, last class it was kind of like this black and white. Does it dissolve or does it not dissolve, right? It turns out that there's quite a bit of gray area in there, and really we can go ahead and ask ourselves, well, how much of a particular compound will dissolve? That's this concept of solubility, right? So solubility, how much of a compound will dissolve in a solvent. All right. There's a few ways to measure, sort of like a few different units that you could use to measure solubility, but by far the most common one is in grams of solute per 100 grams of solvent. All right, so if my memory serves me correctly, sodium chloride has a solubility of about 40 grams per 100 grams of H2O. So what exactly does that mean? That means that you could get a maximum of 40 grams of sodium chloride to dissolve into 100 grams of water. 41 grams, can't get that. You're going to have 1 gram of solid left over. You can get a maximum of 40 grams of sodium chloride to dissolve in 100 grams of water. All right, so that's what a solubility means. Solubility. Okay, so let's just kind of explore this concept. We'll do some easy ones first, and then we'll kind of make it more complicated, all right? So let's ask ourselves, how many grams of solid will remain? Right? How many grams of solid will remain if 20 grams of sodium chloride is added to 100 grams of water, and if 65 grams of sodium chloride is added to 100 grams of water? See if you can't answer these two for me. Say it again.
None will remain in the first one.
Totally, right? So if I got 20 grams, how much solid is going to remain? None of it, right? Because all 20 grams is going to be able to dissolve. That 40 grams is like your threshold, right? That's the maximum amount that you can get in there. Okay? So then if I put 65 grams of sodium chloride into 100 grams of water, first of all, how much is going to dissolve? 40 grams, because that's the maximum. So then how much am I going to have left over?
25.
That difference, right? So that difference between 65 and 40, that 25 grams. So absolutely here, we're below that threshold, below our solubility. All will dissolve. Here, we're above. So 40 grams will dissolve. .25 grams remain solid. Cool? So if you go and you look up any chemical in, you know those big books that they got in the lab? Obviously nowadays everything's been put onto the internet, but back in my day, you had to flip through these gigantic books, and all they did was tabulate all this information about all these chemicals. One of the things that you're going to see if you look in that big book or if you look on those databases about any chemical will be its solubility, right? So you can look up just how soluble a particular chemical is. Typically, water is one of the solvents. Sometimes they have other solvents listed as well, right? But they'll tell you, 15 grams of methanol will dissolve in 100 grams of acetone, whatever it may be, right? So for each chemical, you can look up what its solubility is for various solvents. All right, so let's take this same concept, but we're going to make it a little bit more complicated. So again, how much solid will remain? .65 grams of NaCl is, let's say, mixed. 150 grams of water. Right? So if I increase the amount of water, all of a sudden I've increased the amount of sodium chloride that I can place in there, right? So we're going to have to take our solubility, what we're given, what we just looked up, that 40 grams per 100, and we're going to have to adjust it for the amount of water that we actually have. All right, so how are we going to do that? It's going to look a lot like the stoichiometry that you would have learned last semester. All right, so first of all, my solubility, I can express as this ratio or this fraction, 40 grams of NaCl per 100 grams H2O. So now if I have 150 grams, I got to figure out what that new threshold is, right? So I'm going to take my 150 grams of H2O, and why am I going to multiply it instead of dividing it? How do I know that that's set up correctly? Because you need to pay attention to the units, right? It's all about canceling out those units. If I have grams of water on the bottom, that means I need to cancel it out with grams of water on the top. All right, so grams of water will cancel, and now I'm left with my new threshold, .60 grams. Okay? So then if I place 65 grams of sodium chloride and mix it with 150 grams of water, now how much is going to be, is there going to be any solid that remains? Let's start there. Yes. And how much solid will remain?
5 grams.
That 5 grams, that difference. All right? So I started with 65 grams. I'm going to subtract that 60 grams, which is my solubility. That means 5 grams remain. This is what I start with. This was my solubility. So then this is what remains. Okay. So let's just do one more. Okay. So again, I'm going to have to figure out what my new solubility is, my new threshold, because I have my original, the thing that I looked up, 100 grams of NaCl into 100 grams of H2O. Okay. In order to figure out my new threshold, I'm going to have to multiply that by my 175 grams of H2O. So this tells me that 70 grams of sodium chloride would be able to dissolve in that 175 grams of water. Right? So then my original minus that solubility. All right, so again, this is my starting minus that solubility. This is going to equal 27 grams of sodium chloride is what's going to remain. All right. So again, for any compound, we just stuck with sodium chloride to kind of use the same example and make our lives a little bit easier. But for any compound, we can look it up in one of these chemical databases and see exactly what its solubility is. Again, generally water will always be listed, as well as maybe some other common solvents. All right. This is something that's actually taken advantage of quite a bit in organic chemistry in particular. Okay, so this is the effect of temperature on solubility. Don't freeze. All right, didn't like that. Hold up. Okay. Not this class. Hold up. All right, whatever. We'll just look at it here. So, how'd I do? I guess I was at 100. All right, so first of all, let's look at this curve here. I'm going to make it a little bit less busy at first because I know as soon as you see something like this, it's like your eyes go cross. So let's get rid of some of this stuff here. Let's look at that one. That was a good one. All right, let's look specifically at this yellow curve here. All right, so first of all, on my x-axis, I have the temperature. And on my y-axis, I have the solubility of this particular compound. In this case, it's lead 2 nitrate in 100 grams of water. Okay? And so what happens with the solubility of this compound as the temperature increases? Goes up. Right? So as we increase the temperature, we can start to dissolve more and more of this particular compound in 100 grams of water. All right? So each one of these curves just represents a different compound. Again, this yellow curve here represents this, what's called lead 2 nitrate. All right, we can see we got a bunch of them listed here. Okay? And so generally speaking, it's actually in all but one case here, what happens to the solubility of these compounds as the temperature increases? It increases, right? So generally speaking, the solubility of a solid will increase with increasing temperature. But you see that it's not always the same at all. Some of them increase dramatically with increasing temperature. Other ones, those curves are much more shallow, right? Sodium chloride in particular is a relatively flat curve there, meaning that the solubility at 0 degrees Celsius is very similar to the solubility at 100 degrees Celsius, right? Other ones are like completely different. This one here, the potassium nitrate, starts out with quite a low solubility at 0 degrees, but you just raise the temperature to 50 and all of a sudden you can get a huge amount in there, right? So each solid is different, which is again why this information is tabulated in tables, okay? And you can see that even though it's generally true that the solubility will increase, we got one exception here, one oddball, all right, where this solubility actually decreases with increasing temperature. Okay, so I said that organic chemists, they've sort of taken advantage of this here. So what do I mean by that? Let me see if I can move this. It broke last time, but it would be nice to get it on a different page. Hey-oh, okay. All right, so there is something called a recrystallization experiment. Okay? Where you dissolve a lot of a compound at high temperatures, and then decrease the temperature. All right, so what's going to happen if I take this curve here and I dissolve 70 grams of this potassium dichromate at 90 degrees Celsius, and then all of a sudden I drop the temperature down to 30 degrees Celsius? What's going to end up happening? It's going to come out, right? It's going to start to exactly what we call precipitate. All of a sudden, I'm going to get a bunch of solid that starts to crash out because that solubility decreases. All right? So a natural question is, well, why the heck would you want to do that? It turns out that what precipitates out is of higher purity than what you started with. It's what's called a purification technique. All right, so what precipitates is very high purity. All right, inevitably you lose a little bit of your sample, right, because some of it will remain dissolved in solution. But what you get back is of way higher purity than what you started. So it's a technique that's taken advantage of specifically in organic chemistry quite a lot. All right, so what can we do based on what we just learned how to do with solubility and then using this graph, right? We can figure out just how much we expect to get back. All right, so that's a calculation that we're going to do now. We're going to use this graph. Again, I'm going to try to copy it. All right, so if 90 grams of potassium dichromate is dissolved in 100 grams of water at 90 degrees Celsius, and the temperature is decreased to 20 degrees Celsius, how much solid will precipitate? All right, so given this graph here, given the solubility of this potassium dichromate at 90 degrees compared to 20 degrees, I want everybody to take a second and see if they can't tell me, reading this graph here, how much solid you would expect to precipitate in this experiment. All right, so everybody take a second. Let's convince ourselves here. First of all, at 90 degrees Celsius, I'm at like my max solubility, right? Truthfully, if we're being good, it was a little below that line, but we're just going to round it up here, all right? I drop it down to 20 degrees. All of a sudden, the solubility decreases to 10. So that remaining, that difference, that 60 grams, is then going to crash out, is then going to precipitate, right? So then how much of my sample did I lose in this experiment? 10. 10 of them still going to remain lost, right? And we always like to have high yield, but just as important as high yield is to get a nice pure sample at the end of the day. So there's a little bit of a give and take here. You're going to lose a little bit, but at least what you get back is that higher purity sample. All right? Now, again, we kind of used easy numbers. So let's do the same sort of thing, but now with some slightly harder numbers here. We're going to start out with all right, so everybody take a minute and do this one on your own, and then we'll walk through it together. I'll zoom on this chart so you guys can read it a little bit easier. All right, KClO3, potassium chlorate, so that would be this curve here. All right, and what's really going to make this problem a little bit more of a pain in the butt is I didn't just start you off with 100 grams of water. If it's 100 grams of water, then you can just read the values directly off the chart. But if it's anything other than 100 grams of water, we got to figure out what our solubility would be, and in this case, the 95 grams, right? So that's our first step, is to calculate the solubility of 95 grams at 100 degrees Celsius, and then the solubility of 95 grams, I guess of H2O we can say specifically, at 20 degrees Celsius. All right, so if you had not already, take a minute and do that for me. Okay, so I'm going to call this point here, right, at 100 degrees. I'm going to call this 57 grams. You might have said 56 or 58 or something. It should be close to that, but it's okay if you were a unit or two off. And then I'm going to go look at 20 grams, and I'm going to call this 7 as well, right, or 7 grams. Okay, but this is, of course, the solubility in 100 grams of water, so I'm going to have to adjust that for the fact that we only have 95. So how am I going to do that? Same as we did before. So at 100 degrees Celsius, that's my 95 grams of H2O times that solubility at 100 degrees Celsius. What did I say, 57? 57 grams of KClO3 in 100 grams of H2O. All right, so that's 54.15 grams. So that's my solubility at 100 degrees Celsius. And now I got to play the same game. Oops. And I get 6.65 grams. Okay. So first of all, starting with my initial amount of this potassium chlorate, how much of it is going to dissolve into my water at 100 degrees Celsius? All of it, right? Because I'm below that threshold. I'm below that 54.15 gram threshold. Right? So with this first calculation, we established that all KClO3 will dissolve. Okay, so given what we just did, see if you can't answer the final punchline of this problem here, which is how much solid will I actually get to precipitate? Okay, so importantly, at 0 degrees Celsius, I'm sorry, not 0, sorry, at 20 degrees Celsius, how much of this potassium chlorate is going to remain in solution, is going to be dissolved in my water? The 6.65, right? That's what I figured out. That's the max that you can get into 95 grams at 20 degrees Celsius. So if I originally had 40 in there, and 6.65 remains, the difference, my 40 grams minus that 6.65 grams, that's going to be the amount that I can get back. All right, so this is my initial. This is the solubility. And so this is what precipitates. All right, and again, notice how what we got was that key information from that graph there, right? We had to read that graph in order to be able to correctly answer this problem. I had to get my solubility at 100 degrees Celsius, as well as my solubility at 20 degrees Celsius, and then I had to adjust for how much water I actually had, because these values that you read off the table are for 100 grams of water. All right, so if you're ever sort of doing a problem and you're not sure whether you calculated it correctly, let's just take a step back and do like a sanity check. If I start out with less than 100 grams of water, should my solubility be more or less than what it is on this table? Less. And if I have more than 100 grams of water, should my solubility be more or less than what it is on this table? More, right? So just an easy way to kind of double check that you're doing things correctly. It's not a table, I guess it's a graph, but you know what I mean. All right. So this was, all of these are obviously solids, right? The other thing I guess I want to say explicitly are these are all ionic compounds. How can I tell that these are all ionic compounds? Does anybody remember? Cation and an anion, but how can you spot the cations? They're metals, right? So anytime you have a metal in there and a nonmetal, that's going to be an ionic compound, right? So just something to rewind our brains back to what we discussed in Chem 1A, right? You can spot an ionic compound because it's going to contain a metal, which is our cation, and a nonmetal, or one of these ugly polyatomic businesses here. But the metal's kind of the dead giveaway, right? That we're talking about an ionic compound. All right, so now we're going to go on to gases. Okay. So may or may not be surprising, but gases also can dissolve into solution. All right. One of which we've taken advantage of quite a bit in terms of our beverages that we like to drink, these carbonated beverages, right? They have carbon dioxide gas dissolved in them. Okay, so any sort of a solution can dissolve gases, and these gases have very similar effects, or rather the solubility of these gases, all are sort of uniform in the effective temperature. Can anybody guess what effect temperature has, increasing temperature has on the solubility of a gas? Think about again, just going back to like our soda water, Coca-Cola, whatever it is. On a cold day, does your beverage stay more carbonated longer, or does it stay longer carbonated on a hot day? On a cold day, right? Those things go flat real quick in the Fresno heat, okay? So actually increasing temperature, unlike solids, most solids actually get more soluble as temperature increases. Gases across the board, solubility decreases as temperature increases, okay? Actually, one sort of purification technique for water, if you really need to make sure that you just have pure water, is to heat it up and quote unquote degas it. Get all of any gases that are dissolved, okay? The other thing we're going to explore is the effect of pressure All right, so what do we think? If we have this cup of water and we have some gas, is it going to be more soluble at high pressures or at low pressures? It's going to be more soluble at high pressures, right? The higher the pressure, the more you're basically forcing that gas into the solution. And again, we all kind of know this based on our experience with carbonated beverages. What happens when you pop that can of soda? What do you hear? What's that sound? That sound is that pressure being released, right? So soda is generated at a high pressure in order to keep that carbon dioxide dissolved into that liquid. And as soon as you pop that can, what starts to happen? That carbon dioxide starts to escape, right? Because the pressure of carbon dioxide in this room is much less than it was in that can, right? So again, we can uniformly say it across the board, solubility increases as pressure increases. Oh. Okay. And there's a special sort of law that governs the solubility of gases. This dude, Henry, came along and established this very simple link between the pressure of a gas and its solubility. It turns out that the solubility of a gas is directly proportional to the pressure of that gas times some constant. Okay, so if we're just going to label these terms, this is that solubility, that same term we've been talking about. This is the pressure of the gas. And Kh is just what's called Henry's constant, something that's unique for each gas. All right, so I'm going to put down a few values for KH. These aren't anything that you'd have to have memorized, but you would look them up on a table for your particular gas. Okay. This is really messy. Let me make that prettier. All right. So we see we got pretty different values here for these gases. I want everybody to take a second and see if you can't figure out why they would trend like this, right? So first of all, the value of KH, the larger the value for KH, the more soluble the gas is, right? If you just look at your equation here, if you had, let's say, 1 atm of a gas, right, then the higher the value of KH, the higher the solubility, okay? So which is our most soluble gas here? HF. And which one's the least soluble gas? Helium, all right? So I want everybody to take a second and try to think, why would it be that helium is less soluble than hydrogen fluoride and carbon dioxide is kind of in the middle there? All right, everybody take a second and see if you can't think of why that would be. That might have a little bit of effect, all right? But think back more to what we discussed last class in terms of like looking at structural features and thinking about their interaction with water. All right, let's draw these structures out actually. HF, CO2, and then helium's just friggin' helium, right? Okay. So why would helium be just not very soluble at all in water? It's a noble gas, and what does that mean in terms of its interactions with water? Doesn't really have any, right? It doesn't have any of those favorable dipole-dipole interactions, none of that favorable hydrogen bonding. It's not an ion, right? And then HF being the most soluble. Why would that one be the most soluble in water? Hydrogen bonding, very polar. Right? So it has those hydrogen bonding interactions. So looking at these HF values, they kind of trend with what we were talking about with regard to the structural features that we would expect. If you have strong interactions with water, you're going to be more soluble in water, right? Our noble gases, we would not expect to be very soluble whatsoever. All right. Okay, so then just to do a calculation here, in our last few minutes, I will tell you that the pressure of carbon dioxide in the air around us is about 0.04 atm. All right, and these KH values, I'm pretty sure are moles per molar ATM. Oh, we haven't introduced more. Let's do moles per liter ATM. All right, so previously we were talking about solubility in terms of grams of solute per grams of solvent. It doesn't have to be that. That is the typical definition, especially for solids. You can also do it in terms of moles of solute versus liters solvent, which turns out to be how these values are tabulated. So let's see if we can't figure out the solubility of CO2 just given if we had a cup of water around us, right? So again, I'm going to take that 1.28 times 10 to the 3. And again, this is moles per liter ATM. I'm going to multiply that by the 0.04 ATM. Right, so again, this was our Henry's constant. This was our pressure of the gas. And so that product is just the solubility of the gas. That seems too high. We're going to roll with it. All right, 51.2 moles per liter, which is way too high. So something about that value is wrong. But given what I just gave you, that's how we would do our calculation, right? The pressure of the gas times that Henry's constant will give you your solubility of your gas. All right, and importantly, those are directly proportional. So if I double the pressure of my gas, what's going to happen to the solubility? It's going to double, right? Directly proportional. Cool. What's up? It doesn't have to. It just depends on what units that KH is listed as. So you would just pay close attention to the units of that Henry's constant. Yep. In fact, that was probably the problem here. It's probably pascals. Hey, we recorded.